Drive past a freight yard late at night, and you might hear a massive diesel engine suddenly roar to life. But if you look closely at the locomotive, there is no one sitting in the engineer's cab. A passenger car can be parked, switched off, and left for the night. The lights go dark, the engine cools, and nothing happens until the driver returns. Assuming a freight locomotive can be treated the same way ignores the mechanical reality of how these machines operate. A modern road locomotive can weigh roughly 200 tons and produce around 4,500 horsepower. The primary diesel engine is only the first layer. It turns an alternator, generating the electricity that traction motors use to drive the heavy steel axles. When the locomotive parks, those traction motors stop pulling, but the machine still relies on a network of cooling pumps, control electronics, air compressors, and sensors that must remain within precise operating limits. Shutting down the main engine immediately removes the locomotive's primary source of heat, electrical generation, and compressed air. From the moment that engine goes quiet, 3 invisible clocks begin ticking toward failure. The first clock is temperature. A massive liquid cooling circuit runs throughout the engine block. While running, it carries heat to the radiators, but once stopped, the entire machine begins bleeding heat into the surrounding air. In freezing weather, if that coolant turns to ice, the expansion can fracture pipes, destroy pumps, and crack internal passages inside the engine. The historical solution to this problem was to leave the multi-thousand horsepower engine idling through the night, using its own waste heat to protect the block. Modern idle reduction systems take a different approach. Some use a small fuel-operated heater to warm and circulate the coolant and oil while the main engine sleeps. Others use an auxiliary power unit, a much smaller secondary engine installed specifically to provide limited heat and electrical power. Maintaining internal temperature is a strict mechanical requirement to prevent a multi-million-dollar asset from destroying itself from the inside out. The second invisible clock is compressed air. Freight trains use pneumatic braking, and even stationary air systems slowly lose pressure through microscopic leaks and normal valve losses. An unattended train does not rely on this trapped air pressure to stay parked. Federal rules require physical mechanical securement, like handbrakes, precisely because air leaks away over time. This diagram illustrates a long train's connected pneumatic system. The actual threat is a loss of readiness. If air reservoirs deplete completely, the compressor must slowly rebuild pressure through miles of interconnected hoses before the train can legally move. Even if machinery is unharmed, this slow recharge process renders the locomotive operationally useless until pressure is restored. The third clock is battery voltage. Monitoring equipment and control systems continue drawing electrical power long after the diesel engine stops turning. To manage these decaying conditions, modern locomotives rely on an automatic engine stop-start system, a digital sentinel constantly measuring temperature, air pressure, and voltage. If any of those 3 metrics drops below a critical limit, the system autonomously triggers a command. The massive engine violently wakes up. It runs just long enough to heat the oil, drive the compressor, and recharge the batteries. Once those parameters recover, the system shuts the engine down again. A parked train cycling between noise and silence several times a night is performing a highly sophisticated, calculated self-preservation routine. This explains why 2 visually identical locomotives parked next to each other might act entirely differently. One remains silent because its metrics are stable, while the other starts because an unseen internal threshold was crossed. In the United States, federal emissions rules require new locomotives to use these automatic controls, mandating a shutdown after a maximum of 30 minutes of idling. Those same regulations dictate a specific design requirement. The engine must be able to endure at least 6 automated restarts in a single day without suffering premature mechanical wear. These seemingly random nighttime starts are legally mandated design features, engineered to curb emissions while maintaining strict operational readiness. Freight rail operates at an immense scale. A single train can exceed 15,000 tons, carrying vital food, chemicals, and raw materials between factories and ports. If a locomotive assigned to one of these outbound trains suffers a dead battery or a cold engine and fails to start on command, the entire operation bottlenecks. The railroad must locate a replacement, move it to the correct track, physically connect it to the consist, and rework precise crew schedules around the delay. The automatic system constantly weighs two outcomes: the obvious waste of burning fuel in an idle engine against the hidden waste of breaking the supply chain. The next time you hear a freight locomotive start in an empty yard, the empty cab is proof of success. The machine recognized its time was running out, and it woke itself up to protect the network.